Hey, welcome back. This is the last video about aldehydes and ketones. This is the most important video of aldehydes and ketones and the heaviest one. I appreciate a lot if you give a like to this video because it took a lot of effort to be done. This is going to take a little longer than normal videos, so I suggest to take a cup of coffee if you want. Let's dive in now to the reaction of aldehydes and ketones, that are a lot. Let's start with the first one, oxidation of aldehydes and ketones. So if you use chromium trioxide in acidic medium in 0 degrees Celsius, you can oxidize aldehydes. So you're going to get carboxylic acids. In the case of ketones, this kind of oxidation does not work. It requires strong oxidant in basic medium, but is not widely used as a reaction. You're going to break it here to yield again carboxylic acids for sure. Right? Let's move further. Okay, this is one of the 4 types of classes of organic reactions. Nucleophilic addition. Reaction for aldehydes and ketones are typical. In terms of mechanism, this can be an aldehyde or a ketone. This R' here is going to be a carbon or hydrogen, depends on the reactant that you have. If you treat that with a negatively charged nucleophile, first you are going to move the hybridization of carbon from sp2 that you have it here to sp3 here, and this is called an alkoxy intermediate that is going to be protonated in the next step and to yield an alcohol, and the nucleophile is attached directly to the carbon. The second way is that you have a neutral nucleophile is going to attach again to form the alkoxide, and after that at the end you're going to have the elimination of 1 molecule of water. In this way, for most of the students it's a little bit unclear, but we are going to see them through examples when is going to happen the first one and when is going to happen the second one. Let's move further. The first case of nucleophilic addition that we are going to discuss is cyanohydrin formation. If we treat an aldehyde or ketone with cyanohydric acid in the presence of some salt of this corresponding acid, sodium cyanate, as a catalyst, what we are going to form? We are going to form again the alkoxide, and the cyan is going to attach here, and after that is going to be the protonation by cyanhydric acid and to form halohydrine, OH, CnH, right? This halohydrine formation, this halohydrine compound, if it's treated with lithium aluminum hydrate, is going to be converted to primary amine. So, and if we do hydrolysis of this cyanohydrine, you are going to yield carboxylic acid. Right? Let's move further. Nucleophilic addition of hydrine or reduction. Keep in mind that when we talk for reduction, we add hydrogens to the compound. Okay? It's a trick to remember it. Now, reduction we are doing for aldehydes. If we reduce with sodium borohydrate in ethanol, we can use also lithium aluminum hydrate, but sodium borohydrate works fine. And it is going to give primary alcohol. In case of ketones, it's going to give a secondary alcohol. Right? In terms of mechanism, aldehyde or ketone, consider this sodium borohydrate as an hydrogen. As a nucleophile, negatively charged, it's going to attack here to form the alkoxide, protonated, and after that to form the alcohol. In the case of aldehydes, you're going to form primary alcohols. In case of ketone, you're going to form secondary ketones. Remember it. Let's move further. Addition, nucleophilic addition of Grignard reagent. Grignard reagent is going to add to aldehydes to form secondary alcohols. In case of ketones, to form tertiary alcohols. In case of formal aldehyde, is going to form Primary alcohol, be careful. So, secondary alcohol. Be careful, when we treat with Grignard reagent, we add carbons. In case of sodium borohydrate above, we do not add any carbon, just the hydrogen. Okay, because we are going to see some examples below that needs the Grignard reagent to add more carbons. The second case is going to form tertiary alcohol, right? And with the formal aldehyde, it doesn't matter what is the structure of this, is going to form primary alcohol, in this case ethanol, right? So this is the first stage, and the second stage is hydrolysis to remove the Grignard, to remove the magnesium. Let's move further. Nucleophilic addition of amines, imine and enamine. In case of primary amines, you are going to form an imine. In this case, it's the double bond between carbon and nitrogen. In case of a secondary amine, you are going to form enamine, that is a double bond between carbon that is straight connected with the next carbon that contains a double bond to the nitrogen, right? So, to summarize, if you have primary amine, it's going to give imine. If you have secondary amine, it's going to give enamine, right? Let's move further. If you treat, for example, cyclohexanone with hydroxylamine, what is going to form? This is a primary amine and is going to form this compound, right? Let's move now to the nucleophilic addition of hydrazine. Also called Wolf-Kishner reaction, is important because it's used to remove the carbonyl group. So in this case, you're going to eliminate the carbonyl group and convert that to a normal alkane, right? Because to synthesize this with aromatic substitution, it's hard because you have rearrangement. You need to use acylation first, and after that you can treat with Wolf-Kishner reaction with hydrazine to yield a straight chain. This hydrazine reaction is specific to carbonyl compound because if you have the presence of a double bond is going to remain untouched. So the final product in this case is going to be this cyclohexene, right? Be careful. Do you remember when we use hydrogen in palladium that we reduce a double bond and we keep the carbonyl compound untouched? In this case, it's the reverse. Depends what the exercises want. Okay, let's move further. Nucleophilic addition of alcohols, acetal formation. In case you treat a ketone or aldehyde with two equivalents of alcohol, you're going to yield acetals. So in this case, it's going to be butanol dimethyl acetal, in this case for the naming, but you form this acetal. Why are those acetals important? Because we can use acetal to protect aldehydes or ketones. Take a look at this example, for example. You have a ketone group here and an ester group here. For example, if you want to reduce this ester group and keep untouched this ketone group, you are going to treat this compound to reduce ester with lithium aluminum hydrate. But if you treat that, it is going to reduce also the ketone. If you use ethylene glycol, because instead of using two equivalents, you can use just one equivalent, but because it has two OH, form a cycle with this carbon that contains the ketone group. And it requires hydrochloric acid in a small amount as a catalyst, right? So what is going to happen? This is going to be protected, and you have the right to reduce the ester group. Lithium aluminum hydride in ether and H3O+. So in this case, you're going to have, this remains untouched, the formation of a primary alcohol. And if we do hydrolysis, you're going to remove the ether that is formed here and remain untouched the ketone group. right? For this reason we use acetals. Let's move further. Nucleophilic addition of phosphorus ylide. This is a really important reaction. It's widely generally used in organic chemistry synthesis in the lab. It does not have counterparts in biological pathways, but anyway, it's very handy in the lab. It is called the Witting reaction, or alkane formation from the carbonyl group. So the compound that makes the magic is 3-phenylphosphorus ylide. And here you can have a radical or two, depends on the type of reaction that you want to synthesize. It is also called phosphoran. It can form mono D3 substituted double bonds, but not 4 substituted double bonds. Right? Tetra substituted double bonds are not possible with Witting reaction. Let's take a look at this example. What Witting reaction does, because okay, I explained that beautifully, but how technically you are going to write the reaction. The Witting reaction adds this part to the carbonyl group. It removes the oxygen and adds this part, and the oxygen leave connected with this 3-phenylphosphorus. So in this case, this is going to be like this: double bond CH2 plus, right? What it does, this CH2, it connects that to this oxygen. Always is specific for this kind of reaction and forms alkenes. So let's assume now that we want to go reverse. We want to form with Witting reaction this compound here. Of course, first what we are going to touch is to break this double bond. And one part is going to be the Witting reagent, and after that the other part is going to be the aldehyde or ketone. In this case, we are going to form the Witting reaction with this carbon here that is secondary instead of this carbon that is tertiary carbon. Right? So what is going to happen? So CH minus phosphine PH3. So this is going to react with acetal, and you're going to have the formation of this compound because this is going to attach to this oxygen here, right? How this Witting reagent works or is formed: you start with 3-phenylphosphine and react that with preferably with primary and some secondary halides, because the mechanism of this reaction is SN2 and primary substrates works best. And you form this compound, methyl 3-phenylphosphorium bromide in this case. And in order to make the molecule neutral, we treat with a base butyllithium in THF, and we remove one hydrogen here and remain the structure to make the structure neutral. Methylene in this case, 3-phenylphosphoran. This is the reagent. Okay? Let's move further. Conjugated 1,4 addition. This kind of nucleophilic addition is to alpha, beta unsaturated aldehydes and ketones. Similarly to what we said above, we are going to use those 1,4 in the future videos again. The mechanism is the same, but the attack of the nucleophile here is at the carbon at the beta position. Now, at the beta, because you have the presence of the carbonyl group, otherwise you are not going to attract, the nucleophile is not going to attack to a double bond. Okay? But because the carbon is less electronegative than oxygen, oxygen attracts this pair of electron here, this double bond move here, and leave place makes this carbon more electrophile, and this nucleophile attacks here. And what we are going to form, and you are going to form an enolate here. This is going again to move again to stabilize the carbonyl group, and by protonation of this carbon here, because this double bond cannot move more here because you have the addition of nucleophile. By protonation of this carbon here, you are going to have this compound. The nucleophile is added to the beta position. Let's see in action. Conjugate addition of amines. In this case, you have a conjugate addition 1,4. Why? Because 1, 2, 3, 4. So the amine, instead of attacking here, is going to attack here, right? So what you're going to have, this remain untouched, and here you're going to have the formation of the amine, right? In case of Grignard reagent, is not going to have the same effect. The formation of the alcohol is going to be here. In case of this reagent that we call Grignard reagent, the organocopper compounds, here you are going to see the CH3, right? This remain untouched. Okay, let's move further. Let's move to the exercises. Exercises are perfect for organic chemistry. Exercise number 1, you have to carry out all those steps. I prefer to go reverse because imagine if it's given only this and this compound and you have to go reverse. So to simplify things, I wrote all the intermediate compounds to go to this stage. So now here we have an aldehyde, and if we go back, is converted to a primary alcohol. So from primary alcohol to go to aldehyde, what we treat? We treat with what? It's a oxidation, Des-Martin periodion in dichloromethane, right? Or PCC or PDC, doesn't matter what you use, it's the same. Now, from this Grignard reagent, you want to go to this alcohol, that is primary alcohol. Do you remember from Grignard reagent, the only compound that forms primary alcohols is formaldehyde. Be careful, right? It's formaldehyde. Remember this small compound because it's important, right? And H3O+. Let's move again back. From this halide to form Grignard reagent, sure you're going to treat with magnesium in ether. You should know this. And from this primary alcohol to the halide, you're going to treat with those two special reagents. What was that? Thionyl chloride or phosphorus 3-bromide. In this case, is phosphorus 3-bromide in ether. And to move from aldehyde to primary alcohol, in this case, you're going to do reduction. And how we did that? With sodium borhydrate, treated with H3O+. Right? Let's move to the second exercise. Now, from this compound to go here, let's go reverse again. This is what? Enamine, right? As we learned. And this ketone, to form enamine, it needs to react with a secondary amine. But this is a cycle, so this is already a secondary amine. What we are going to add here? A secondary amine. And with H3O+. In acidic medium, you're going to add this compound to form enamine. After that, from this ketone, it has gone to a secondary alcohol. From secondary alcohol to ketones, what we do? This is an oxidation, so we can use chromium trioxide in H3O+, right? And after that, from this alcohol here, we are going to aldehyde. Be careful because you have addition of 1 carbon. So the reaction here should be Grignard reagent. So what is the Grignard reagent? CH3MH, Br, and hydrolysis. Right? Let's move to the last exercise. Now here, start from here to here. Now here you are going to break this one here, and the part that is forming the Witting reagent is this one, so the ylide. And this part here that should react with this to form this double bond here should be cyclopentanone, right? Because this oxygen is replaced with this group here, right, to form this compound. Let's move back now from this compound to go to this compound. Now, this is treated with what? First, this is a primary halide that we need to form the Witting reaction here, the Witting reagent. So, what is going to be formed? What is going to be reacted with 3-phenylphosphine first, and the second butyl lithium, right? To remove 1 hydrogen. And we yield this compound. Now, from this to this compound, sure, you know again, primary alcohols, phosphorus 3-bromide in ether. And from this compound to this compound, from aldehyde to alcohol, In this case, we do not have addition of any carbon. So what we are going to do, we are going to do reduction with sodium borohydrate in H3O+. Right? And I think we are done. So thank you so much for watching and hope this video helped you, and look forward to see you in the next video. Peace.